Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 7.2 titled Asymptotic Growth of Functions. Alright, so in this section we're going to see compare how two types of functions grow, the rates at which they grow in relation to one another. All right, and this is as the value of the input increases. How fast or how slow does one type of function grow when compared to another type of function? All right. All right, so again, I'm gonna read this to you. There's a lot to take in. This may be new to some of you. So suppose f is a function that maps positive integers to positive real numbers, right? So a function from z plus to r plus. The asymptotic growth of the function f is a measure of how fast the output, f of n, grows as the input n grows, right? So it's asymptotic growth of a function is a measure of how fast the output grows as the input grows. Okay. All right. The classifications of functions using O, omega, and theta notation, called asymptotic notation, provides a way to concisely characterize the asymptotic growth of a function. Asymptotic notation is a useful tool for evaluating the efficiency of algorithms. So we talked about algorithms, right, in section 7.1. This concept of asymptotic growth is tied heavily into determining how efficient one algorithm is over another. But we're not going to really get into that, but still, it's, this notation, this asymptotic notation, is introduced here. So you have what's called big O notation, big omega notation, and big theta notation. I'll probably just say O, omega, and theta, but in some videos you might come across some other books. It's big O, big omega, big theta. Alright, so I start off here with the big O notation. So the notation f equals O of g is read, f is O of g. When you say f equals O of g, that essentially means that function f is less than or equal to g if constant factors are omitted and small values for n are ignored. I'll write out in my own words what big O and omega and theta notation mean later. So in the expressions, 7n cubed and 5n squared, right, the 7 and the 5 are called constant factors, right, because the values of 7 and 5 do not depend on the variable n. So if f is O of g, then there is a positive number c such that when f of n and c times g of n are graphed, the graph of c times g of n will eventually cross f of n and remain higher than f of n as n gets large. Okay. So I'm going to read all this stuff, right? This is pretty heavy. So consider the function, f of n equals 2n cubed plus 3n squared plus 7. There are many functions, g of n, such that f is O of g. For example, f of n is O of 4n cubed plus 2n plus 1. However, the idea is to select the function g that characterizes the asymptotic growth of f as simply as possible. Therefore, G is selected so as to eliminate all unnecessary constants and additional terms. So instead of saying that f, right, this 2n cubed plus 3n squared plus 7, instead of saying that f is O of 4n cubed plus 2n plus 1, one would typically just say that f is O of n cubed, right, like the highest order term in that polynomial. Right. Sometimes the functions in this material will evaluate to a negative number, such as n divided by 2 minus 10, when n is less than 20. In order to ensure that every function maps to a positive number for every possible input from z plus, the output value can be replaced by 1 if the output is less than or equal to 0. Thus, the function f of n really means whatever the maximum value of f of n in 1 is at any particular value. Just to ensure that we go positives to positives, positive inputs to positive outputs. Alright, so here's what this big O notation means. And again, I'm going to write it out in words on a piece of paper, what this means. So let f and g be two functions, from the positive integers to the positive real numbers. Then f is O of g if there are positive, if there are positive real numbers called c and n sub 0, such that for any n in the any positive integer n, such that n is greater than or equal to n sub 0, f of n is less than or equal to c times g of n. Alright, on a piece of paper I'm going to write out what this means in words. Okay, so this is, so again, sometimes referred to as big O notation. So when you say that a function f is O of g, this means that some positive multiple, right, this means that there exists, means that there is, some positive multiple of g that is eventually larger than f. And when I say eventually, this means as you move to the, as you increase the inputs to infinity, at some point, the graph of, this positive multiple of g will be higher than the graph of f forever. So this means that there is some positive multiple of g that is eventually larger than f. Right. So on a graph, x or n, I guess, he's using n instead of x for the inputs, and then the output, y or something. So suppose here is the graph of f. Say that's the graph of f of n. If you say that f is O of g, that means that, some positive multiple of g, say call it c times g, right? C times g of n, where c is positive, eventually, at some point, as you move to the far right, is eventually larger. So maybe like this. Maybe c times g of n starts off down here, but then at some point in the future, some point as you increase the inputs, c times g of n starts becoming larger than f of n and stays larger than f of n. And then this value here on the horizontal axis, this is that n sub 0 that they're talking about. When they said that there's some positive value c and some positive real number n sub 0, such that when I take values of n greater than or equal to n sub 0 here, when I take values of n greater than or equal to that, you see how from then on, from n sub 0 onward, this positive multiple of g is greater than f. So f is O of g just means that there is some positive multiple of g that is eventually always bigger than f. Eventually larger than f. And I think they draw a similar picture here in the activity. So here, for instance, f of n is 2n cubed plus 3n plus 7, as they mentioned this up here, right? This f. And they want to show that f is O of g, where g is n cubed. So you see they got the black graph here is the graph of f. That's the graph of 2n cubed plus 3n squared plus 7. Or 2x cubed plus 3x squared plus 7. And then the blue graph is some positive multiple of g. Now, for polynomials, it's pretty simple. 2n cubed is the lead term of f. So basically any multiple of n cubed that's greater than 2 will eventually be larger. Alright, so that's why they're doing 3 here. If I pick c to be 3 and look at the graph of 3n cubed, you see the graph of 3n cubed is at some point always larger than the graph of f. And at that point is at, n equals 4 or n0 equals 4 here. So for any value greater than or equal to 4, you're getting, f is greater than or equal to c times g of n. I'm sorry, less than or equal to, f is lower. Right, so after, so for any n greater than or equal to 4, f of n is less than or equal to, 3 times g of n. But there's a positive number c and a positive number n sub 0, such that when you're beyond n sub 0, f is less than or equal to cg. Right, that multiple of g is eventually larger. Now, it didn't have to be these numbers. It didn't have to be 3 and 4. Let me show you another. I got the Desmos website here, desmos.com. It's a free online graphing calculator. So let me put up f. All right, f of x equals, and that was, what was it? 2x cubed. Yeah, 2x cubed plus 3x squared plus 7. All right, 2x cubed plus 3x squared plus 7. All right. So maybe I'll make this bold here. All right. Let's look over here where things are positive. All right. So this red graph, right, you see you got the x-axis down here, y-axis. Looking at the positive inputs, starts increasing pretty sharply. And I see what they did was they said, hey, let's take y equals, and the function g, right? The g that they were looking at was n cubed or x cubed. And they said, oh, let's just take 3x cubed, something with a coefficient larger than 2. And you see that eventually that blue graph eventually increases to the point where it's higher than the red graph. Alright, this is pretty rough here, but alright, I'm gonna pause this and get to a point where, okay, and like here I've scrolled up a lot more to like 171 here. And you see now the blue graph, 3 times x cubed, is now eventually is higher than the red graph, and it stays that way the rest of the way. And if you find where they meet, let's go back out here. And you kind of look at, hey, where does that happen? Where does that change? Looks like around. Blue is still higher than red there. And then we're getting closer, closer. And then here it looks like they're about the same. And then blue is lower than red. So somewhere in here, all right, there's the switch where the blue graph starts surpassing the red graph. And you see how that's about 3.5. So they just say, hey, let's take number 4, right? So definitely at the number 4, at x equals 4 here, the blue graph will definitely be higher than the red graph for the rest of the way. But I could have made that a little easier. All right, let me go back to the main screen here, the main graph, and I mean, instead of using 3x cubed and x equals 4, looking beyond 4, I could have picked really anything. I could have said, hey, pick a 10x cubed. 10x cubed, and then you see right away, beyond x equals, now that's 1.09. So I just say, hey, beyond x equals 2. Beyond x equals 2, the blue graph will be higher. Right. I could have also made it real easy and just use 12. And we'll talk about that in a second. Look at 12x cubed, and you see when x equals 1, they meet, right? Because they'll both have an output of 12, and then the graph of 12x cubed is going to be higher the rest of the way. So I could have had c be 12, and then that n sub 0 be 1, and then beyond 1, the graph of 12x cubed is higher. So you'd say that f is O of g, O of x cubed. F is O of x cubed, or O of n cubed. Yeah. Okay. So yeah, it's a little tricky, but it doesn't have to, like I said, it doesn't have to be these numbers that they chose. I could have had c be 12 and n0 be 1, or I could have had c be 10 and n0 be 2, or 1.5, or 1.1, whatever that was. All right, so here they give an actual proof of an example of a proof. Let me actually I'll write this out for us. All right, let me prove that this particular function is O of g. All right, so I'm going to go to a piece of paper. So here f of n is 3n cubed plus 5n squared minus 7. G of n is n cubed. We're trying to prove that f is O of g. Or in other words, show that 3n cubed plus 5n squared minus 7 is O of n cubed. Right. Okay. Again, you could play around, right? Now, this is not a proof, what I'm about to do. All right, I'll come back and actually write a proof. But we can play around with a graph. All right, so I go here, and I'll go back to that Desmos site. And I'm going to graph, f equals 3x cubed plus 5n squared, 5x squared, minus 7. All right, so that's the red graph there. And then notice, I could use I could use 12x cubed. Remember the graph, the g was n cubed or x cubed. Look, 12x cubed is seemingly always larger. All right. So I could use 12. And I'll go over some suggestions for you. I think an easy one though would be 8. 8x cubed is when x equals 1. 8x cubed is always higher. right? Just basically anything with a coefficient higher than 3. Really, I'm going to do 8 because of the 3 plus 5 here, because the x squared might add on some value to this. But if I make it 8x cubed, then that's always going to be higher than 3x cubed plus 5x squared. Right. But there, I found a number 8 and a number on the number line 1, such that beyond 1, the graph of 8x cubed is always greater than f. Okay, so what we're going to do is we're going to prove that this function f is O of g. So remember what that means. That means we need to find. Right, so we will find a positive pair, positive number c and a positive number n0 such that for every n greater than or equal to n0, right, from n0 onward on the number line, the following will happen. F will be smaller, less than or equal to c times g. Right. Well, like I said, I think my choices are pretty clear from my graphs earlier. I'm going to pick 8, so I'm going to let c equal 8, and we'll see that n0 equal to 1 will suffice, and n0 equals 1. Right. Now, starting with f here, 3n cubed plus 5n squared minus 7, right? That's definitely less than, because just get rid of this negative 7 here, because if I add 7 to this, it makes it bigger. So 3n cubed plus 5n squared Alright, and then for all n greater than or equal to 1, for all n greater than or equal to this 1 here, this n0 I chose, multiplying both sides by n squared would be greater than or equal to n, and multiply by n again, you got n cubed would be greater than or equal to n squared. So if I change n squared to n cubed, it just makes this larger. So this would be less than or equal to 3n cubed plus 5n cubed, or 8n cubed, and there we go. I have shown that f of n is less than or equal to, right, this less than or equal to here, some positive constant times g. And this is for all n greater than or equal to 1. There's your n0. Right, so there's your c, positive number times g there. There's your n0. And you can see that again in the graph. Right, you can see that, and then I'm done. Right? F is O of g. I should have stated that as well, that f is O of g. But again, you can see that in the graph. That, 8 times x cubed just after x equals 1. Right? Just after x equals 1 is already higher than the red graph, right, than f. And they give you some suggestions too. Oops, I want to do this. So they got that there. They got proof here. There's another video explaining the steps in the proof if you want to watch that. So now the constant c and n0, right? That I chose 8 and 1 there. In the definition of O notation, are said to be a witness to the fact that f is O of g. So when a proof that f equals O of g, there are many different choices for c and n0. Right? Like I said, I didn't have to use 8 and 1. I could have used 12 and 1. I could have used, since this lead coefficient, the lead in this, is a polynomial with the highest power term is 3n cubed, I could have used 4n cubed for g, the 4 times g. 4n cubed would eventually be bigger than this, but maybe not after 1. I'd have to go through and prove, figure out where it would be larger. But 4n cubed would eventually be larger than f. So I could have used 4 for c and then found whatever n0 was necessary so that after n0 that 4 times g would be larger. So the proof above had c, c equals 8, n0 equals 1. C, I could have had c be 4 and n0 be 5. That would have also worked. After n equals 5, the graph of 4 times n cubed would have been larger than f. The algebra and the proof would have been more involved. Sure, okay. Alright, so in showing that a polynomial function f of n of degree k is O of n to the k power, you can use these as witnesses. n0 equals 1 and c equals the sum of the positive coefficients of f, including the constant term. Alright, so they say, for example here, if you wanted to show that this polynomial function was O of n to the fifth, that some positive multiple of n to the fifth is eventually higher than the graph of this function, you could use the sum of the positive coefficients, 3 plus 7 plus 2, that's 12, and then n0 equals 1. And the proof would be very similar to what I showed you. So I'm going to do that actually on some paper. All right. Okay, so here was f, and g this time is n to the fifth. We're supposed to show that this function here is O of n to the fifth. That means that some positive multiple of n to the fifth is eventually larger for forever, right? Beyond some value n0 is eventually larger than f. So again, what they're saying is you can do this pretty easily with polynomials, right? With polynomials only. Just have that c be the sum of the positive coefficients. So if I let c equal 3 plus 7 plus 2, I let c be 12, then you can just let n sub 0 be 1. From 1 onward, the graph of 12n cubed would be higher than the graph of f. Now look at f, right? F is this 3n to the fifth plus 7n to the fourth, minus 3n squared n cubed plus 2. Now, this is a negative term for n greater than or equal to 1, right? This is a negative term for n greater than or equal to negative 1, greater than or equal to 1 here, this n0. So if I get rid of it, if you add 3n cubed, you're just going to make this larger. So this is less than 3n to the fifth plus 7n to the fourth plus 2. Right. And I guess you could call this 2 times 1. So, we got n greater than or equal to 1 here. We're looking at 1 and beyond. Our n0 is 1. Well, that would mean that n squared would be greater than or equal to n. N cubed would be greater than or equal to n squared. N to the fourth would be greater than or equal to n to the third. N to the fifth would be greater than or equal to n to the fourth, right? So if I replace n to the fourth with n to the fifth, it's going to make this, as big or larger. And through this chain of inequality here, you can see that 1 is also less than or equal to n to the fifth. So I can replace the n to the fourth with n to the fifth, replace this 1 here with n to the fifth, and it'll just give me an expression that's as big or larger. So this is less than or equal to, 3n to the fifth plus 7n to the fifth plus 2n to the fifth, which is my 12n to the fifth. And there you go. I've just shown you that f is, smaller than some positive multiple of g beyond some point, right? And this is beyond n equals 1 here, right? So f is less than or equal to 12g, for all n greater than or equal to 1. Therefore, f is O of g. This function is O of n to the fifth. So for polynomials, it's really that simple. You can just have the constant c be the sum of the positive coefficients, and then your n0 be 1, and then you can easily prove. All right, so suppose these functions here, f of n equals 5n to the sixth minus 4n to the fourth plus 2n squared plus 4, and g of n equals this, right? Indicate whether the following statement is true or false. Right, so for any n greater than or equal to 1, the value of f of n will be less than or equal to 11n to the 6th. Well, is 11 the sum of the positive coefficients there? 5, 2 is 7 plus 4 is 11. Yeah, this would be true then. For n greater than or equal to 1, f of n would be less than or equal to 11n to the 6th or 12n to the 6th or anything higher than that even. But from what we saw up here, this is true. How about for n greater than or equal to 1? Would g of n be less than or equal to 9n to the 6th? Well, let's take the sum of the positive coefficients here. That would be 10. So no. All right, now I'll say this though. This function g would eventually be less than 9n to the 6th because the lead coefficient's higher, right? 9 to 4, but not at n equals 1. It'll be a little later on down the road. But if I replace 9 with 10, then this would be true for n greater than or equal to 1, right? So this is false. Then you can check it, see when n equals 1, g is 10, but this right side would be 9. That wouldn't be a true statement. Is it true that f of n is O of n to the 7th? Well, yeah, this is a 6th degree polynomial, right? This is a 6th degree polynomial. A 7th degree polynomial is definitely going to be eventually larger than a 6th degree. So yes. And again, you could just use 11 and 1 there. All right, now how about the other way around? Now, how do we prove that a function is not O of g? So remember the definition here. They had it up top. By definition, if function f is O of g, then there must be a witness, right? There must be these positive numbers. There exist positive numbers, c and n0, showing that f equals is O of g. So showing that f is not O of g requires showing that every possible combination of values, every c and n0 that are positive, fails to work. Because this is a there exists statement. And remember, the opposite of a there exists is a for every. So if you're trying to show that a function is not OG, you have to show that for every positive value c and every positive value n0, f is not OG. F is greater. All right, what's the opposite of the statement up here? It would be f is greater than c times g of n for values of n greater than or equal to n0. All right, so I'll write that out. All right, and then take you through this example here, and I'll read it out. I'll play the end. Oh, I have that right here actually. So a proof that f is not O of g must establish that for every n0 and c positive numbers, right? For every positive n0 and c, there is a value of n greater than or equal to n0 where f of n is not smaller than the multiple of g of n, right? Where f of n is bigger than the multiple of g of n. All right, so all this is saying, and I'll write this on paper. If f is not OG, right, O of g, so f is not O of g, means that every means that every positive multiple of G is eventually smaller than F. Well, or equal to F. Is eventually less than or equal to smaller than F. Well, I'll say less than F, right? That was the F is greater than. No, so just less than C times G. Okay. So this is, again, every positive multiple of G is eventually less than F. Okay. So now they do these examples where they prove that F is not OG by contradiction. Now remember, a proof by contradiction. A proof by contradiction means you assume the opposite is true. So if you're trying to prove that F is not OG, first assume that it is. Assume that it is. And then if that leads you to a contradiction, something that is and is not at the same time, something that can't happen, then that means that your assumption was wrong and the function actually isn't O of G. Alright, so I'll play this here for you. So I have F is n cubed over 2 minus 2n squared plus 3. Now this is a degree 3 polynomial. Degree 3. G here is a degree 2. Now a degree 3 polynomial will grow faster than a degree 2. So no matter what positive number I multiply this by, it's still a degree 2. So n cubed, a degree 3 will always eventually be bigger. So that's the explanation. In words, what we're saying here when we say F is not O of n squared. All right, so they say, hey, let's prove this by contradiction. Suppose that F is O of G. That means that there is some constant c and some number n sub 0 such that for all n greater than, n past n sub 0, F is less than or equal to c times n squared. All right, then they run through and kind of manipulate this a bit. Right, you can get you can get rid of the 3 really. Because say if I get rid of the 3, that makes this term smaller. So this expression in the middle here is greater than or equal to just n cubed over 2 minus 2n squared. And then they divide everything by n squared, right? Because n squared would be a positive number that wouldn't change the inequality. And they multiply by 1 over n squared. And then kind of solve this for n. And then you see how n would have to be 2c, less than or equal to 2c plus 4. Right. Now, let's think about this. We're saying that the original assumption was F is OG. So for n greater than or equal to n0, this must happen, right? There must be some c and some n0 such that when n is greater than or equal to n0, this is happening. Right. And then you get down, and then wait a minute. So for n greater than or equal to n0, we also have n is less than or equal to 2 times c plus 4. So it's greater than or equal to n0, like it said for all n greater than or equal to n0. But this wouldn't be true for values beyond 2c plus 4. But we just said for all values greater than or equal to n0, this should be working. But then this is saying it won't work for values beyond 2c plus 4. So whichever one's bigger, n0 or 2c plus 4, anything beyond that, it won't work for. So this contradicts the fact that you have to this has to work for all n greater than or equal to n0, because it's not going to work for n greater than 2c plus 4, right? So it can't be both, right? So you got a contradiction, and therefore f is not OG. Now again, you can with polynomials it's easy to tell. It's easy to tell. Look at the degrees, right? If they're the same degree, great. Then one will be O of the other. If the degree of f is larger than the degree of g, g is never no positive multiple of g will grow bigger than f. So f is not OG if f has a degree higher than g. But if it has a degree less than or equal to g, then you can say f is OG, and you saw that in previous examples. All right. So as I mentioned, they're just telling you here, hey, what do you need to prove when you're saying that a function is not O of something? So a proof that f is not O of g must show that it is not the case that there are positive constants c and n0 such that for every n greater than or equal to n0, f of n is less than or equal to c. So basically they're saying what is the opposite of this. So remember that's for every c and n0. The opposite of this for there is for every. The opposite of this for every is there is, and then the negation of this would be greater than. So that's the second statement. Right? For every choice of positive values c and n0, there is a value of n greater than or equal to n0 such that f of n will be greater than c of n, c times g of n. So again, they go through the notation here, the there is and for alls and negating it. So take a look at that. Now, you don't have to prove this or disprove it. Just think about it. These are polynomials again, very easy. Is n squared O of n? Now this is a degree 2 polynomial, and n is a degree 1. Could you multiply n by a positive number and have it eventually always be greater than n squared at some point? No. N squared grows faster than n, any multiple of n. So no. They go through, they show you the proof and everything, but just think about it. Now another way you could think about O notation too is that f is O of g if g grows at least as fast as f, as fast as f or faster. Any multiple of n won't grow as fast as n squared, so that's why you're not O of n. All right. Now this next notation. All right, that was a lot, right? A lot of time there on O notation. You have omega notation. This is big omega. All right, so the O notation serves as a rough upper bound for functions, right? Again, disregarding constants and small input values. The omega notation is similar, except that it provides a lower bound on the growth of a function. All right, so this big omega notation says let f and g be two functions, again from the positive integers to the real numbers, positive real numbers. Then f is omega of g if there are positive real numbers c and n0 such that for any n greater than or equal to n0, f is greater than or equal to c times g. So f is omega of g. So this means that so if f is omega of g, that means that there is some positive multiple of g that is eventually smaller than f. Right? For O of g, it was that positive multiple of g was eventually bigger than f. This is just the other way around. the positive multiple of g that we're looking at is eventually, after some n0, is eventually smaller than f. Now another way you could think about this, and I'll show this to you later, if f is omega of g, that means that g is O of f. I think they're right there here, yes. So if f is omega of g, then g is O of f. All right. So if you want to show one, you can show, we've been showing O's. If you want to show that f is omega of g, you can just show that g is O of f. That's not wrong. All right, but they do go through here some examples of proving, using this definition of omega, proving that a function f is omega of g. So again, I'll read off their suggestions. Now this is again for just polynomials, really. We'll get to other kinds of functions at the end of the section and talk about growth rates. So here, in a proof that f is omega of g, again, there are many different choices for c and 0 you could use that would work. But if f of n is a polynomial of degree k, then f is omega of n to the k only if the coefficient of n to the k of the n to the k term in f, say a to the k, is positive, because it's got to grow eventually, right? If the lead coefficient of f is negative, then it's not going to go up. It's going to go down at some point. Here are the combinations for c and n sub 0 that will suffice as witnesses to show that f is omega of n to the k power. All right, so like earlier, some nice suggestions here so you don't have to do too much thinking. All right, you could always go and do some thinking, look at graphs and whatnot, play around with it, but I'd suggest just coming back to these. So if f has no negative coefficients, then you can have c be the lead coefficient and n0 be 1, and you can show that f is omega of n to the k. If f has negative coefficients, but again, the lead coefficient must be positive in order for it to be growing eventually bigger than some multiple of g, right? Then let capital A be the sum of the absolute values of the negative coefficients in f. And then the choices are, let c be half of the lead coefficient, and then your n0 be whatever the largest value of 1 or 2 times a divided by the lead coefficient is. So there are examples here. Suppose f is 1/7 n to the 6th plus 2n to the 5th plus 3. You can show that this function is omega of n to the 6th by just taking c equals 1/7 and n0 equals 1, right? There's no negative coefficients in this. So 1/7 times n to the 6th is going to be smaller than this function after n equals 1. Right? So there's your multiple of n to the 6th that's eventually smaller than f. So f is omega of n to the 6th. And then this one, this one has negative coefficients, but again, positive lead coefficient, so it's eventually getting big. If f is 7 n to the 6th minus 2 n to the 5th minus 3, then I could take again half this lead coefficient, 7/2. Now, you could take really any coefficient smaller than 7. 6 n to the 6th would eventually be smaller than this. Right? It would. 6 n to the 6th would eventually be smaller than this. Just might be a while, right? It might not be after n equals 1 or 2. So that's why I'm just saying, just take these suggestions up here so you don't have to do too much thinking or do any algebra or something like that. So take c equals half the lead coefficient, 7/2. So we're looking at the graph of 7/2, 3.5 times n to the 6th. And n0 equals, 2 times, now remember this a here was the sum of the absolute values of the negative coefficients, -2 plus, this is 2 plus 3, that's 5. That's 10/7. And whatever the largest of 10/7 and 1 is, well, 10/7 is bigger than 1. So if you looked at the graph of 7 halves n to the sixth, after 1 3/10, that graph will be lower than f for the rest of the way. Right. So again, pretty, a little tricky, but doable. Again, I'll let you read the proof here. And like I said, if you want to prove that f is omega of g, you could prove also that g is O of f. Same thing. All right, and then go through a couple more examples there, blah, blah, blah. All right, cool. So then, based on the information they give up here in these couple proofs you're going to be reading, indicate whether each statement is true or false. The values c equals 1 and n 0 equals 1 are sufficient to show that f equals n cubed plus n is omega of n cubed, right? So this is saying that 1 times n cubed is going to be smaller than f after n equals 1. Right, from n equals 1 onward is going to be less than or equal to f. Yes, those are all positive coefficients, so yeah, I can have c be just the lead coefficient and n be 1. Yes, this is true. This one has negative coefficients, so the absolute value of all the negative coefficients added up is just 3/4. And 2 times that. Yeah, it's 2 times that divided by the lead coefficient. So 2 times 3/4 is 3 halves divided by 1, and then the largest of 1 and 3 halves is 3 halves. So this wouldn't be enough. I can let c be a half, right? Half that lead coefficient. But then the n sub 0 would have to be 3 halves, right? From 3 halves onward, the graph of half n cubed would be lower than this. Would be lower than f. So this is false. I need to have n sub 0 be a half. And yeah, you can play with the last one. All right. So now the last notation. Right, so you got this. F is O of g if some multiple of g is eventually bigger than f. F is omega of g if some multiple of g is eventually smaller than f. All right. So let me write this stuff out. All right. What it means in terms of growth rates. Right. So if f is omega of g, O of g, that means g has a growth rate equal to f or greater. G has a grows or has a growth rate, grows at a rate equal to or faster than f. And then when you say f is omega g, this means that g has a growth rate equal to or slower than f. G grows at a rate equal to or slower than f. Right. So then this last notation, you're going to see is f equals theta of g, big theta. This is just both. This is both of these. So g and f have similar or equivalent growth rates. It doesn't mean they're the same function, but they have the same kind of growth rate. Right? They'd be going up at about the same rate as each other. So this one's g is faster or equal, g is slower or equal, and then g and f have equivalent growth rates. So the theta notation indicates that two functions have the same rate of growth. So again, functions from z plus to r plus. F is theta of g if f is O of g and f is omega of g. Alright, so if you want to prove that a function is theta of g, you need to prove both of these, right, from earlier. Right, to prove that f is O of g, right, so prove that some positive multiple of g is eventually larger than f, and prove that some positive multiple of g is eventually smaller than f. You know, greater than or equal to, less than or equal to. I keep saying larger and smaller, but really it's greater than or equal to, less than or equal to. All right, and then another definition here. If f is theta of g, then f is said to be of order g or order of g. So for example, you know, any degree 3 polynomial is order of n cubed. You know, any degree 4 polynomial is order of n to the fourth, and so on. Right. And the terms, you know, in this polynomial here, 7n and 16 are called the lower order terms, because removing those terms would not change the order. All right, so I've already mentioned any degree k polynomial is order of k, n to the k. Right, theta of n to the k. All right, so some examples. Now pay attention. Really pay attention to the degrees, right? The higher the degree, the faster your growth rate. Right? The faster you shoot up as the input increased. So f is degree 5, g is degree 1, h is degree 2. So f has a higher growth rate than h, and h has a higher growth rate than g. Right? It would grow faster than g. So the first question is f omega of n to the fourth. So would, you know, some positive multiple of n to the fourth eventually be less than f, or is the growth rate of f higher than n to the fourth? Yeah. Or is the growth rate of n to the fourth lower than f? Yes. Because f is a degree 5, so this is true. Now is f O of n to the fourth? So is the growth rate of n to the fourth higher or faster than f? No. So higher degree is going to be a faster growth rate. Is g theta of n? So are they the same degree, same growth rate? Yes. And g is degree 1, n is degree 1. Yes. And is h omega of n squared? So does n squared have a smaller growth rate, a slower growth rate than h? Well, h was degree 2, so yeah, well, less than or equal. Right? I keep saying smaller and greater. It's less than or equal. Yeah. All right, now we're going to talk about some other functions, right, other than polynomials. All you're taking away from this part here is that logarithms with numerical bases, logarithmic functions, all have the same growth rate. So a log base 2 function has the same growth rate as a log base 7. Because you can use the change of base rule and change everything to base e, you know, some constant multiple, you know, log base e, natural log. So every log function with, you know, constant bases, you know, base 5, base 7, you know, with actual number bases, not variables, have the same growth rate. So looking at this, you know, which function is not theta the log of n? This is log base 10, right? So which of these functions don't have the same growth rate as the log of n? Well, this is log base 17. You know, again, logs with the same base have the same growth rate. This is log base 1.001. You know, it's just a number base. They have the same growth rate. Right? Again, logs of any base, base greater than 1, I should say. Base greater than 1 have the same growth rate. And this one here, the base is not a number. It's something with another variable entirely. So this would have a different growth rate than those logs. Alright, and then down here, I'll just skip over all this. You can read that. We have a list going from the lowest growth rate functions to the highest. So constants, right? Now you've seen the graph of a constant. I think they even have a little picture down here. No, they don't. Okay. So let me draw these. Right, the graph of a constant is just flat, right? There is no growth, so it's definitely got the slowest growth rate. And in fact, let me see if my let's go to 17. So say this is the xy axis here. You know, constants. You know, like y equals 1, y equals 2, just no growth. All right, there's your constant functions. All right, the next one in the list is the log of the log. All right, the log of the log. Now that would start off at like, if it's log base 10, it would start off at 10, 0. And then you wouldn't get up to 1 until you got to 10 to the 10th power, which is way out there. You know, 10 to the 10th power, you'd get 1. So like, it's growing, but very, very slow. That's the log of the log. All right, log. Very, very slow. All right, and then logs themselves, just plain old log, you know, you'd have 1, 0, 10, 1. Those grow faster. Logs, you know, shoot up faster than logs. Logs of logs. Then linear functions. All right, linear functions like y equals n, shooting up like that, right? There's a linear. Grows even faster. All right, then n times log n. N times log n. Now that would start at 1, 0 here. But eventually shoot up and eventually grow faster than the linear. So it's eventually faster. N times log n. Right. Then you have your other degree polynomials. You know, linear is a degree 1 polynomial. Then you have your quadratics. You know, then you have your cubics. So grow even faster. And 4th degree, 5th degree would be even faster. Then your exponentials. Now I know they start off slow. Exponentials start off slow, but the exponentials eventually shoot up faster than any polynomial. Like 2 to the x, 3 to the x. Exponentials with a base bigger than 1, I should say. All right, c to the n, where c is greater than 1. Exponentials with a base bigger than 1 will eventually shoot up faster than any polynomial will, any degree. It could be a degree 100 polynomial. The exponentials will grow faster. And then finally, you know, factorials. Factorials. This is a terrible drawing. But remember, factorial is like, you know, 2 factorial. N factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to times 3 times 2 times 1. So like, for example, 5 factorial would be 120. You know, it's 5 times 4 times 3 times 2 times 1. 6 factorial would be 720. 7 factorial would be 5040. And they go, you see how fast they get quickly? 5040. And then, you know, 8 factorial, it would be 40,320. I mean, it gets big fast, and faster than your exponential functions do. So that's what this table is. It's telling you the type of function and its growth rates from slowest to fastest. Slowest to fastest as you go from top to bottom here. All right, so all you really have left to do, well, let's see, you know, just again, compare growth rates based on the type of function. Based on the type of function. So like, is 2 to the n O of n cubed? Remember, 2 to the n is an exponential. n cubed is a cubic, a polynomial. Exponentials will eventually grow faster than polynomials. So this is false. Remember, if one function's O of another function, that second function is the faster growing one, or equal to. Faster or equal. So this is false. Right? Is an exponential omega of a logarithm? Yes. Remember, if you're omega of a function, then the function inside the omega has a slower or equal growth rate than the function before it. So this is true. Is n to the 20th O of, now 1.1 to the n. This is an exponential. It's going to have a faster growth rate than any polynomial. So this is true. Right? Remember, if you're O, that means the one inside has a faster growth rate. The other way around, no. Right? The 1.1 to the nth will have a faster growth rate, not slower. And if you're inside the theta, that means you have a slower or equal growth rate. Okay. Then you can read these rules here and play around with this. I'm not gonna. You can mess with these. All right, those are all pretty similar. And then your challenge activity is just putting things in order. Right, so again, you can just keep referring back to this list. Keep referring back to this list, and all you're doing is putting functions in order based on growth rate. So I'll show you a first example here. You got a factorial. That's the fastest. Factorials grow crazy fast, so I'm going to put that first. You see it's greater than or equal to. This is growth rates. Linear, Now this, I know there's a seventh power here, but there's numbers. These are all numbers. This is a constant. So that's definitely going to be the slowest. I'll put this at the end. All right, b of x. Then you have your linear and quadratic. The quadratic's going to go faster than a linear will. So d of x second, c of x third. And now I've got them in order from fastest growth rate to slowest growth rate. And again, you can refer back to that chart often if you wish. And I think this is all like that. Yeah. So you got another one where you're given types of functions. Now, if you have a sum, the term with the faster function dominates. The term with the fastest growth will dominate the growth. So here I have something that's like n times log n. Remember, this grew faster than a linear. And the linear grew faster than a log, but x squared. Now, there's an x squared and a log in this one. Remember, the term with the faster growth rate will dominate. So this will grow like an x squared will. The log won't matter so much when x gets large. So the quadratic has the largest growth rate here, the one with the quadratic term, so d. All right, then again, your n log n, x times log x, this will have the next fastest, so a, then the linear, b, then the logarithm, just the plain old logarithm, c. So in order from fastest growth rate to slowest growth rate. And again, I think that's what all these look like. Let's look at level 4. Yeah. So again, if you have a sum, like d here, the factorial dominates. This is going to have a factorial growth rate, fastest. Here, the faster of these two is the n log n, x log x. So this will have a growth rate like this one. This is a cubic, the fastest one of these two, and this one. These are both logs, so it's just a logarithm. Because remember, the sum of two logs, I mean, yeah, I could get this to be a single log. This is just a logarithmic growth rate. So again, just pay attention to what's the fastest, what's the slowest, and if you want, keep referring back to this chart here for, rates of growth for different kinds of functions and how they compare. All right. Then you have your additional exercises. Now, in some of the additional exercises, I do want you to prove that a function is, theta of something. Now, if you want to prove, now these are just polynomials, so remember they gave you little tips up earlier how to prove these, what you should choose for c, what you should choose for n0. So go back and refer to those if you want to write these proofs out. Now, the thing is, you gotta be careful. If you want to prove that f is theta of n to the 5th, You got to do both. You got to prove that f is O of n to the fifth and prove that f is omega of n to the fifth, and do the same thing for part B. I think I got both those in the assignment. All right, and then this is proving that you're not, prove that something's not O or not theta or not omega. And if you recall from earlier, if you want to prove that something is not O or not omega, try by contradiction. Suppose that it is O, suppose that it is omega, and then hopefully that leads you to some sort of contradiction like in the proof earlier with the animation that I showed you. Alright, yeah, so then, again, I don't think all of these are assigned, but I would still recommend looking at all the problems, checking the solutions, once you've tried to work through them on your own first, of course. Check the solutions after, see how you're going. Don't just copy solutions, it's not going to learn anything that way. Yeah, so that's it for this. That was a lot. All right, again, it's another long one. But now that we're going to be out of Chapter 7, there's only these two sections in Chapter 7. Hopefully the videos will get a little shorter, because there's a lot to explain here, right? Big O, big theta, big omega, all those. Asymptotic growth rates, and this is something you probably you usually don't see like in an algebra or pre-calc or calc class, so probably the first time any of you are seeing this, unless you're taking computer science. You've probably seen this before. Okay, all right. Well, hopefully this is a good guide for you when you read through and work on section 7.2 on your own. Obviously, if you have any questions, shoot them my way. Let me know. And thank you very much for watching.